All right, good afternoon, everyone. Any questions before I start? So for those of you who haven't submitted your homeworks, if you could please do that like right away. So both the labs and the homeworks, we'd like to get them looked at and returned to you as fast as possible. I changed the URL for the slides. If you go to the one that you went last time, it'll redirect to this one here. So now it's on GitHub. So if you want to follow along, load them now, either by going to this site here or the one that you've had last time. So today we have a busy day, so let's just get going with it. We'll start with something that's probably familiar to you if you've had a course in Haskell or ML or the like. So you know that functions are values, and we've exploited this relentlessly. So when we write a function, we always write it as an anonymous function first, and then we put it into a variable. So these things have types. The type of a function is the name of the parameter type, then an arrow, and then the name of the return type. So this is an int to int. And what can you do with the function? Well, there's a couple of things you can do. The first thing is you can call it, of course. You could just evaluate what triple is. But more importantly, what you can do with the function is you can pass it to another function. And so that's the whole idea of functional programming, that whenever you have some bit of functionality, some bit of code that you want to pass around, then you can simply do that. So here we are using map, and we're passing the triple function to map. And map applies that function to every element. So map is what's called a higher order function. It is a function that consumes another function. And so that sounds maybe confusing, but one doesn't think about it. There's nothing really tremendous going on. The function is a value like any other, and so why shouldn't it be consumable? Another very important higher order function is filter, that we're going to be using all the time. And in fact, no one complained about that, but I think you needed to use filter for one of the homework assignments. In the future, if something like that happens, just drop me an email and then I'll send out clarification. So filter takes a function that returns a Boolean. So that in this case, this is a function from int to Boolean, and then it keeps everything for which that function returns true. So the function that I have here checks whether a value is even, whether it has remainder 0 when you divide by 2, and then we retain all the even elements here when we call filter. So in this case here, notice that I passed the function directly. I didn't bother to even give it a name. I simply passed this block of code to filter. So this is a function that consumes another function. We'll soon see functions that produce other functions as well. Before that, a little bit of Scala syntax here. When you define a function, normally you specify the parameter type. So over here, when we define triple, we had to say that x is an int. In Haskell, you don't have to do that. In Haskell, it'll infer what the parameter type is, but there are reasons why that's hard to do in Scala. So in Scala, only the return type is inferred. So in this case, we don't have to say that the return type is int, because obviously, if x is an int, then 3 times x is also an int, and that's inferred. But there are many situations where the parameter can be inferred, particularly when you pass a function to another function where from the type of some other parameter, we can exactly tell what x has to be. In this case here, this is a range of int, so each of the elements is an int, and the type inference then knows that this x here must be an int, and you don't have to write it. And so we don't want to have to write unnecessary stuff. As an extra bonus, that if you only have a single set of parentheses, a single parameter inside the parentheses, like you have here, then you don't even have to write the parentheses. So here it's just x without the parentheses. And the super bonus is that if you have a parameter that occurs exactly once on the right-hand side, over here, then you can instead of giving it an explicit name like x, you can instead call it underscore. And so you can write this function as 3 times underscore. It is the fervent belief of every Scala programmer that every keystroke is precious, and you want to write everything with as few keystrokes as possible. And so this is what Scala programmers will do. In fact, in a couple of lectures, you will learn about another way of squeezing, I think, another keystroke out of here. But for today, this is as good as it gets. All right, so and it reads actually very nicely, right? 3 times underscore is the function that multiplies stuff with 3. And so you're passing that on to map, and what you get is everything multiplied by 3. So let's look at another higher order function. It's called reduce. It's very useful. So reduce takes a function, and this is a function with 2 arguments, and then it applies it to the elements in a sequence in turn. So recall that S parentheses 0 is the first element, or I guess the initial element, the 0th element of a sequence, and so F gets applied to that. Then we take the result of this, add S2, and apply it to that. So all of that is very abstract, so we'll just look at a special case. Let's say we reduce by the function underscore plus underscore. That's a binary function. It's a function that takes 2 elements and adds them to each other. So if I had to write it by hand, I would write it as xy gets mapped to x plus y. But of course, underscore plus underscore is the same thing, just much shorter. So when you do that, then you first compute 1 plus 2. Then the result of that gets joined with 3. The result of that gets joined with 4, and so on. So that's what's called reduce. And as you can see here, that applying plus to reduce just gives you a sum. Here you have a slightly different function. This function here computes the larger of A and B, and if I do that to a whole sequence, then I get the max of the sequence. So we'll be using reduce quite a bit. And here we have a quick exercise. So do we have our voting cards? So for those who joined us for the first time today, the way the voting works is that you get a card, and you pick one, put it in front of you, and after a minute or so I say, now please all hold up your votes or turn over your votes. Yeah?
Yeah. Is there a mechanism like in Haskell where we can use operators as functions?
Yes.
So that we can only
But you can't like write parentheses plus that you can do it in Haskell. So I guess the mechanism really is the underscore mechanism. So that the underscore plus underscore. That's as a mechanism as it gets. But what we'll see a little later is that Haskell has an actual difference between operators and functions, and there is no such difference really in Scala. That any binary function is an operator. All right, so can we see what our votes are? Okay, we have a C, we have a B, another B, another B, and another B, another C. So a whole bunch of B's and C's, and it actually is C. So why can't it be B?
because there is no space.
That's right. See, B has a bunch of spaces here, and there's nothing in here that produces the spaces. So all it does is it puts 1, 2, 3, 4, 5, 6, 7, 8, 9 without any intervening spaces. And if you think hard about it, that is exactly 192 characters. Right? It's almost 200, and you lose a few because of the ones. All right. So, but I mean, basically the idea is clear. So what this, so the key here is we first map to strings, and then we concatenate all the strings. So the plus here means concatenation, and because we're operating on strings, and it just smashes them all together. There's actually an easier way. If you wanted to do this, there's a function that does this. This is just an exercise to see what reduce does, and to see whether you're awake after lunch. All right, so reduce is a useful function, but there are situations when reduce doesn't quite cut it, and and we'll learn a couple more functions that that deal with that later today. But another useful function that happens all the time is called flat map. So let me actually run the REPL really quick here. Because it's otherwise a little unintuitive. So let's have a sequence of integers s. And now what I'm doing is I'm getting all of these pairs. So I'm mapping so that the comma 0 gets appended to the end of each of the pairs, of each of the entries. So I have everything with the 0 in the second coordinate, and that's nice. But what if I want to have something slightly different? What I would like to be able to do is I would like to have all the pairs x, y where the elements in my sequence. So an obvious way of trying to do something like that would be to call map twice. So I have this. And instead of putting the 0 here, I'm going to put a y. And where does the y come from? It would come from here. So and when you do that, then what you get looks perfectly right. You get all of the combinations of the various elements. But what's wrong about it? Yeah. What's that? That would be my fault. Yeah, because there's duplicates here. So let me choose a different sequence here. Put a 0 in here. Okay, good point though. So now we've gotten rid of the duplicates. But what's wrong with it? It's the embedded vectors. It's not really what I wanted. I want to have a sequence of all of the x and y's in a single vector. But now what I have is a vector of vectors. So I need to flatten that vector out, and that's what flat map gives me. So when you call flat map, then it takes the results and it all puts them together. So let's just try that here. And then you see we get a single vector. Okay? So when using flat map, you kind of have to work yourself inside out. Notice that when I wrote this expression, I started in the inside and worked my way out. And so the flat map has to be the one that's the outermost, because you first have to have something that you can flatten. So in general, the map goes inside and the flat map goes outside. So hang on to that thought. You'll need that a little later. Another thing that you're probably familiar with is is capturing variables. But let me go through this in some detail. So here we have a situation where I define a function fun, and it multiplies x with n, where n is defined outside here. And that's perfectly okay. Any function in Scala is perfectly happy to capture stuff from the enclosing scope, so the n here gets captured fine. There is a little bit of something special going on, and so let's look at this function here. So we have a function called mul_by, and this is a function that returns a function. So when I call mul_by4 over here, then that returns a function, namely the function that multiplies x with 4, the n over here. So that's why I called it quadruple. And so when you call that, it's a function. It takes an argument that then becomes the x here, and so it multiplies that with 4. So each of these when you call mul_by4, you get one function. When you call mul_by3, you get another function. And each of them has a different value of n, and so it's a good question. Where are those n's stored? So think of quadruple, and now make another call in your mind. Val triple is mul_by of 3. Then each of those here is defined by this code, but each of them works with a different value of n. And so the way that works is that a function is not just the code of the function, it's not just the body of the function, but it's the body plus some data structure that resolves what's called the free variables. So in this expression here, x is bound by the parameter, but n is a free variable, and so that has to be defined somewhere. And so the way it works in an object-oriented language, there's a little object that carries that information that's bundled together with the code of the function. Such a thing is called a closure. So a closure is the implementation of the function plus the binding of its free variables. And it's not something one really has to hugely worry about. It's just you have to understand that it is common in any functional language for a function to capture variables from the outside. So we actually used this feature, and no one complained. So in which of these slides did we already use closures? In which of these slides did we define a function that captured something from the outside? So have a look at both of those slides and pick your card. So I figured this was maybe a little bit more intricate. So let me again tell you what I mean with what's a closure. A closure is a function that captures some variable from its enclosing scope. Like over here, this n, it's nowhere defined inside this function. So this function here has to know what n is, and it has to carry the captured n with it. And of course, the n comes from out here. So when we look at the reduce slide, or the flat map slide, see if a capture like that occurred. All right, does everyone have an answer? Yeah, let's see. Okay, good. So the majority vote seems B with a couple of C's and D's. B was the flat map. Now flat map for sure. So what gets captured? Y. So it's in this function here, this little thing inside here, the x maps to xy, where x is defined, that's a parameter, but in that expression, y is not defined. Y was captured from here. Okay? Now, And so you said S, and that's also true, right? Because this S here gets captured from the outside. So there's two things that got captured. All right, let's see in reduce. Did anything get captured? No, I don't think so. Because now you, for one thing, we didn't even write a function. So, yes. So really, there's nothing. All right. So that was the right answer. All right. So that's the lab. I'm sorry, that's the lecture. So this lab is going to be somewhat long, and so to make sure that we get through it, I was going to say a couple of words before we get started. So first, we'll start out with something that's fairly simple, where you avoid looping by using maps, and so that's pretty similar to the homework. I think you'll have no trouble with that. We'll practice reduce, and I think that's also fairly straightforward. And then there's this longish exercise where that we're going to be going through in various stages, where we're solving a problem that Martin Nudersky likes to solve in a different way when he gives like an introductory Scala presentation and wants to show off the power of Scala. So in this little project here, we're going to be mapping from phone numbers to words. So in the United States, this is particularly common. Like there is a company that sells flowers by phone, and their phone number is 1-800-FLOWERS, F-L-O-W-E-R-S. All the American phone numbers have 7 digits, and so you just tap out the word flowers on the phone key. And so if you wanted to do something similar, you might have a phone number and you want to see, is there a snazzy word or a sentence that is associated with that number? And so that's what this thing here gives you. So for example, say you have the phone number, this is a good American number, 435-569-6753. You say, well, that's hard to remember. But if you actually knew that this spells out the sequence hello world, out of a sudden that becomes a very easy number to remember. But how do you find that out? And so that's what this program does. And it's going to go on in various stages and put these things in a worksheet and carefully save them from one lab to the other. This is going to go through 3 different labs and name the functions exactly so, because I refer to them later. So here's a function that's supposed to be called words4, and it really does need to be called like that. So get going with that, and then we'll compare notes at the end to make sure that we're all at the same stage, because otherwise you can't go on to the next. So let's get going. Everyone has a buddy today. I guess the 2 of you could work together, and then we'll have an even number.